Hey guys, how's it going? In this video, I'm going to go through this Leetcode 460 LFU Cache. And this question was asked by Amazon for 20 times in the past 6 months, and also Microsoft 8 times in Google and other. So let's dive into this question and to see what it's asking. So we need to design and implement a data structure for a least frequently used LFU cache. So this question is related to another question, LRU, which is a least recently used cache. If you haven't seen that question and haven't tried that question, I recommend you to try that first because it's related to that question. So implement the LFU cache class. LFU cache in capacity initialized an object if the capacity of the data structure. So that's a maximum data we can store. That's a capacity. This is a function get and get the value of the key if the key exists in the cache. Otherwise, return a -1. Also, another function put and update the value of the key if the key has already existed, or insert the key if that is not already present. When the cache reaches the capacity, it should invalid and remove the LFU, least frequently used key, before inserting a new item. For this problem, when there is a tie, in other words, two or more keys with the same frequency, this is where you use the LRU. The least frequently recently used key would be invalid. And to determine the least frequently used key, a use counter is maintained for each of the keys in the cache. The key with the smallest use counter is the LFU key. When a key is first inserted into the cache, its use counter is set to 1 due to the put operation. The use counter for a key in the cache increment either a get or a put operations to call upon. So basically what it says is whenever we call the specific key, and the use counter will increase by 1. The function get and put must run in a big O 1 or average time complexity. So immediately from here, we can know that we must use some sort of hash data structure, either a hash map or a hash set, which when we retrieve the data, it takes a constant time. So let's look at some example in here. And we first have a counter, and also we have a cache, and the cache will showcase the last used order for tiebreakers. Leftmost element is most recent. So from this, we can know that we might need use a doubly-linked list, which was used in the LRU question. So to initialize and we will have to use the same thing in this question LFU. So the LFU cache, this is where we initialize the object. The capacity is 2, and this is where we put the first key and its value. And so key being 1 and value is being 1, and then we put another one, key being 2, value being 2. So now you see the cache, and also the counter. Counter of 2 has 1, and also counter of 1 has 1. And cache keep track of the keys, right? So now we have 2 keys, and this is where we retrieve the data. And so we calling the key of 1 and return the 1 because this is how we put it at the first place. And now after we call the key of 1 for the first time, so the counter will increase by 1. So now the counter for 1 will be 2, and counter for 2 will remain as 1. So now the cache, the position of 1 will increase by 1 to the most recent, and now 2 is the least recent. And then now we put another data, which is a key of 3 and value of 3. So 2 is the LFU key because the counter is only 1, which is the smallest. So we have to get rid of 2. So invalidate the key of 2. So now the cache, the most recent is 3, and the least recent is 2. And again, the capacity is only 2, because it's how we initialize it at the beginning. So now the counter of 3 is equal to 1, and counter to 1 equal to 2, because again, we first created the key of 1, and then we call it. So we use the key of 1 actually 2 times. And now we have already got rid of the key of 2. Now when we call the key and return a -1 because we already deleted. And then here we getting the value of the value for key of 3 and return a 3. And now we getting it, we calling it, and we increase the count from 1 to 2. Also the count for 1 it remains at 2. And now 3 remains to be the most recent. And then we insert another key of 4, has a value of 4, and both 1 and 3 has the same count, but the 1 is the least recent, and so we get rid of 1. So we have the rooms for insert the key of 4. So now 4 is the most recent, so it's stay in the head of the cache. So the count of 4 is equal to 1, and count of 3 remains as 2, because we just created it and we have not yet called it. So the count remains 1. And then now we're calling the key of 1, and we're going to be return -1 because we already deleted in the prior step. And now we're calling the key of 3 and return a 3 because that's how we insert it as first place. And now the count of 3 will increase from 2 to 3, and count of 4 remains to be 1. And now the key of 3 will most recent, so we update the position at the cache. Okay, and then we're calling the key of 4, and then return the value that corresponds to the key of 4, and we increase the count 4 from 1 to 2, and the count of 3 will remains of 3, and also we have to update the position. Actually here, the 4 would be the key of 4 should be most recent. That's why the position of 4 should be here, I think. But anyway, I think this is small error in the example, but you get the idea. So now let's take a little bit on the design to see how can we tackle this question on. So we need 2 dictionaries in here. This graph at the first glance may be difficult to understand, but actually it contains a lot of information. That's why when we break it down, actually it's not too bad. So let's take a look at it. So again, we need 2 dictionaries. One is called self.free. So we keep track of the frequency because this is where we use the. So this is where we keep track of the count that we saw earlier. And then another one is called self.node. So this is the key. So basically it ties to the node. The key being the key. I mean the key of the dictionary being the key of the data, and the value being the node. By node I mean the doubly-linked list. And in here for this dictionary, the key being the frequency, being the count. So for example, 1 corresponds to the count 1, 2 corresponds to the count 2. The value is a doubly-linked list. So the difference between these 2 dictionary, the key is not the same. I mean the key of the dictionary is not the same, and the value is not the same, but they are serving the 2 different purposes. And this diagram, I think, does a very decent job to convey that information. So as you can see, the value it points to a the D-linked list, right? So so the first D-linked list corresponds to a contains all the elements that have a count of 1, and the second D-linked list contains all the elements of which have a count of 2. And for the dictionary on the right, so as you can see, for data has a key of 1, and it points to that node. Okay, and for data that has a so I should say a key value pair that has a key of 2, and that points to the nodes that has the key of 2, and so value is 2 and frequency, etc. So And also when we look a little bit closer to the nodes, so that we can see how we can initialize the data structure. Okay, so the nodes, we need a 1, 2, 3, 4, 5 different elements. The key, the value, also the frequency, which is the count, and also the prior, also the next. And this is how we initialize this data structure. So yeah, so this is the bird's eye views on how we can implement the data structure. If you like, feel free to pause this video and try it yourself. Next, I'm gonna implement on Python to see. So we first need a class of nodes. We can create some object. So class node, and we first create the init dictionary. So it carries the key, value, frequency, also the prior, the previous, and the next. Okay. Oops. Okay, there we have it. Let's fix the indentation. So once again, each of the nodes, it has its own key, own value, also frequency, which is the count. Initially, we have the count of 1 already. Also, it has a property of a previous, also the next one. And initially, we have the none, just a starting. And the next one, what we need is the Doubly-Linked List. Oops. We can call it just D-linked list, okay? Which will contain all the nodes and connected by the previous and the next. So it's very similar to a single linked list, but this one has can go 2 directions. And for that, we need a few things to initialize it. We need a dummy head. We can initialize the value as a none. Doesn't really matter here, just the dummy values. And also we need a dummy tail. So everything that's closer to the dummy head will be the most recent, and everything close to the dummy tail will be the least recent. After that, we also need a size to keep track of how many elements in that D-linked list. Okay. And then we need a helper function to let us know how many members are carried by the D-linked list. So this is the helper function. After that, we need another helper function called append. Okay. Where we will append a new element, new member to the D-linked list. So whenever the new member comes in, it's always the most recent. That's why it just comes closest to the dummy head. Okay. So this is the helper function for append. And as you can see, the new member next will be equal to the dummy head dot next, and the previous will be dummy head itself, because now it's the most recent. So after we build connections for the node itself, and we have to build connections for the head. So whichever is the last one, the last most recent one, which is the dummy head on next, and this is the prior most recent one. Previous will be the newest member, and the dummy head dot next equal to the node itself. Basically, these 2 lines in here, this line and this line. Oh, sorry, and this line and this line. They are building the directions, the Doubly-Linked List. And after these 4 lines to insert the newest member, and we have to increase the size by 1. This is this line. Okay, so this block of code is how we can pop off the least recently used node. So if the size is 0, so we do nothing, so return a none. Else, that means we have at least one element, and the LRU node will be the one that closest to the dummy tail. Because once again, the one that closest to the head is the most recent. The one that closest to the tail will be the least recent. And right now, the one that before the tail will point to the one that before the node, before the LRU node. So this is how we can squeeze out the LRU node. Okay. At the same time, so essentially this guy over here, this is the second least recently used. And then the second least used node, next one now points to the tail. And essentially what these two lines is doing is to squeeze out the LRU and building the connections between the tail and the second least recently used node. At the same time, after we squeeze out the LRU node, we decrease the size. Also, we return the LRU node at the same time. And we don't need this DL node. This is some scratch code that I created myself. And now we can implement the LFU Cache class. And also we don't need this block as well. It was for me for this, doing some experiments. So I actually modified this function a little bit. Now I call it only pop LRU. This is because this is exactly what it does. And also I created another helper function named pop, and which pops of a specific node, which is very similar to this pop LRU. If you want, you can combine these two functions into one single function. But I just want to make it more clear. That's why I'm writing two separate functions. Very similar to the prior, we just basically squeeze out the given node, and at the same time we decrease the size. So the given node dot periods dot next. So the one before that, the next one will point to the current node dot next, and also the current node dot next the periods pointer will point to the current node dot periods. At the same time, we decrease the size by 1. And if the size is 0, we just do nothing. Okay. Again, nothing fancy in here. So now let's dive into the LFU Cache class. So let's walk through some initialization for the LFU cache class. The cap is equal to capacity given, and the node is a dictionary. Again, as we talked about before, the key being the key of the data, value being the node, which is this object class. Also, we have a frequency dictionary, which is the key being the frequency, and the value is the D-linked list. That's why I have the default deck here. Also, we need the minimum frequency. This is used for pop off the LFU when we need it. So let's look at the get method. If this key is not already exist, we just return a -1. If it is in the node dictionary, and we first call the node by look up the dictionary. So we put in the key so they come back with the node that we're looking at. And there's a property of the frequency of the node, which is called frequency, which this is why we need this property, the freq. And so the current frequency equal to the node dot frequency. And now what we do is update the priority. Also, not priority is updated. Yeah, it's also priority as well, which we will update in here. But first, we have to update the count, right? So we look at the old D-linked list by look up the frequency dictionary, input in the frequency key, and then we pop off the current node and then we insert it to the new linked list. And where's the new linked list come from is after we update the frequency. Okay, so for example, the old frequency is 1, and we remove from the linked list that correspond to the frequency of 1, and then add it to the frequency. Now the frequency will be 2. Okay, and then we insert it to the linked list that has a frequency of 2. Okay, and also at the same time, we may have to update the min freq property of the LFU cache. So if the min freq equal to the current frequency, so we update it. Okay, because we have to do it again, this same operation, and we might as well just put in the update helper function. So we call it update. Okay. Self, and also we need the key as well, and we don't need to update anything, return anything. So what we need is all this. Awesome. And now what we need to do is just call the function self.update. Changing the spacing, and there it is. Again, because we need to use this function again in the put method, that's why I just create another helper function. Just make the code a little bit cleaner. Okay. So now let's implement the put function. Okay, so this is the implementation for the put function, and if the key is already exist, basically we just update the value, also update the position, also the frequency. So that's why we implement this updating as a function, because we will use it again here. Otherwise, if this is a new key value pair, and then now we check the capacity. If the current capacity is already at the cap, and then we pop off the LRU, and also look at the least frequent. So this is the least frequent linked list, and then we pop off the LRU, so we return the LRU back, where we need a key to remove from the node dictionary. At the same time, after we pop off the LRU, actually in this case it's LFU, right? It's the minimum frequency, at the same time it's LRU, and then we decrease the size by 1. And now we can insert the new node. We insert to the node dictionary. At the same time, we insert to the frequency dictionary. Look at the frequency of 1 because it's newly created. So the frequency is the default of 1. Append it to the dictionary by the new node. So now the minimum frequency will be 1, which comes from the newly created node. At the same time, we increase the size by 1. Okay. Let's try and run that. Okay, I'm going to pause the recording and then fix some bugs in here. Probably some just time. Okay, now I've fixed some code. Now it works, and pass all the 24 test cases. So what I did was, first I forgot to type the type property, which keep track of how many values, key value pairs in total. So that's, and secondly was here, we have to check. This cover one of the test cases where if the capacity is 0, we don't have to do the rest. We don't have even insert it because we are the capacity given is 0, so we don't even need to insert anything. So that's the second thing. And the third one was here to when we initialize the D-linked list, we have to build connections between the head and the tail. So these two lines, so head.next equal to the tail, and tail.periods equal to the head. So this line I missed. And sorry about that if you're coding along, and I will post the complete code in the description down below. And for time complexity is big O1 is required, and for space complexity mostly it comes from the two dictionary. One is the this guy right here, note, and another one is the frequency dictionary. So most of them take up a space of big O(n). So for space complexity, big O(n). So this is so much for my solution. I hope this is helpful. If it is, please like and subscribe. That would be a huge encouragement to me. Thank you so much for watching. I will see you in the next video. Thank you.